Hello everyone, today we'll discuss chapter 3, namely Thermochemistry of Fuel-Air Mixtures. Some of the topics are a review of the topic you learned in Thermo 1 and Thermo 2. This is the content of chapter 3. The first subtopic is Characterization of Flames, and then Ideal Gas, Air and Fuel Composition, Combustion Stoichiometry, and then first law of thermodynamics. So these four topics have been studied in Thermo 1 and Thermo 2. So this is in Thermo 1 and this one is in Thermo 2. And then the last topic will be the introduction of the chemically reacting gas mixture. Let's take a look on this first subtopic, namely characterization of flames. Combustion process inside the engine cylinder controls engine power, efficiency, and emission. And it is necessary to know this combustion characteristic in order to understand the engine operation. The combustion process is different between the spark ignition and compression ignition engines. In the spark ignition engine, the combustion process is initiated by a spark generated between the spark plug caps, and then a flame kernel is created by this spark discharge and propagates across the cylinder to the combustion chamber walls. And then at the walls, these flames will be quenched or extinguished as a heat transfer and also destruction of active species at the walls become the dominant process. And then we might have also a self-auto-ignition ahead of the flame front, and this self-auto-ignition or auto-ignition can generate engine knock, which due to the high pressure generated can lead to the engine damage. And then in the diesel engine, we have a fuel that is injected into the cylinder, and inside the cylinder we have air, or maybe air plus EGR, already at high pressure and temperature, because this fuel injection is near the end of compression stroke. Then the auto-ignition or self-ignition of the portion of the developing mixture of already injected and then vaporized fuel with the hot air start the combustion process. And this will spread rapidly. And then this burning process proceeds as the fuel and air mix to the appropriate composition. So it should be within certain range from the stoichiometric mixture composition. Thus, we will see that the fuel-air mixing process plays a controlling role in the diesel combustion process. So, therefore, sometimes a diesel combustion process is also called mixing control combustion process. The combustion process is a vast exothermic gas phase reaction where oxygen is a critical reactant. In the actual engine combustion process, we won't use a pure oxygen, rather we'll use oxygen within the air because it is free. And then a flame is the region within which the combustion reaction takes place, which can propagate subsonically through the space. So it means that the flame propagation speed is below the speed of sound. So in the next slide, we will see the structure of this flame. Flame classification can be based on the condition of the mixture. So we might have a premixed flame. This is the case for the spark ignition combustion process. So when the spark is ignited, around the spark plug gap is a premixed mixture, of the fuel, air, and maybe EGR. And then we might have a non-premixed combustion. So this is the case for the diesel combustion. So we have air inside the engine cylinder, and then we inject the diesel, and then the combustion occurs maybe several crank angles after the injection process. And then we might classify the flame based on the bulk flow. So in this case, we have a laminar flame, and in this case, the combustion process occurs at lower Reynolds number, and the molecular diffusion process control the combustion speed. And then the next one, we might have a turbulent flame. So in this case, the bulk flow motion of the mixture enhance the combustion process, and this is on top of the laminar combustion process. And this bulk flow is represented by the average flow plus the fluctuation flow, and usually we use a parameter of turbulent kinetic energy to represent this fluctuation flow. And then we might classify the flame as the steady flame as well as the unsteady flame. So in the steady flame, we have a steady flame structure, and then for the unsteady flame, the structure of the flame might change with the time. And what is the flame types inside the engine? Inside the engine, either we have a premixed, turbulent, unsteady flames. This is for the spark ignition engine. Or we might have non-premixed, turbulent, unsteady flame. This is for compression ignition combustion process. This is the schematic of the flame characteristic for a premixed flame. So we have temperature as the vertical axis, and then on the horizontal axis we have a distance here. So this is a distance from, let's say, the center of the flame front. So it is somewhere here. So there are three zones here. Zone number 1, it's called preheat zone. And then zone number 2, it can be called reaction zone. And then zone number 3, so this is actually inside the burn zone. So in this case, we assume that the flame is stationary. So it's mean that the observer is moving with the flame. And then on the left side, we have unburned zone. So it's mean here we have a fresh mixture of air, fuel, and maybe EGR. And then on the zone number 1, we have what's called a preheat zone, because there will be a heat transfer from right going to the left. And inside the zone number 2 is where we have a reaction process taking place. So in this case, there will be a release of the chemical energy into the thermal energy. So it increases the temperature, it increases the pressure. Therefore, there will be a heat transfer from zone number 2 to zone number 1. Similarly, there will be also a heat transfer from zone number 2 to zone number 3, which is in here is the burn zone. So inside this burn zone, we have almost 100% gas product from the combustion process. You can also see in here the temperature profile. So we have TU here. This is the unburned gas temperature. So which is mainly the compression temperature. So it can be like 700, 800 Kelvin. And then because of the heat transfer from the reaction zone, the temperature increases here. So you can see in here going to the right, it increases. And then we have TI, so we can call this one is the ignition temperature. Okay, and then the temperature still increases here inside the reaction zone because of the chemical energy release. and then TB will have some maximum temperature somewhere inside the burn zone, which is close to the center of the flame front. Okay. And then the next profile here is showing the chemical energy release. So the maximum energy release is somewhere here. So it is inside zone number 2. So what is the thickness of this zone 2? Is a very thin. Okay. And then this is the characteristic of the laminar premixed flame. How about the characteristic of the turbulent premixed flame? It is shown on the right side here. So this feature shows several short time scale realization of a turbulent premixed flame. So in this case, the fuel air mixture flow out of the tube. So this one is assuming this is a tube. And then so we have a fuel air mixture exiting the tube. Okay, and then through the wrinkle thin flame sheet. So you can see this is the wrinkling flame, and because of this wrinkling process, the turbulent flame speed is much higher than the laminar flame speed. But you will see, or if you want to see this turbulent flame speed in more detail, that locally at each point of this turbulent flame sheet, the laminar structure is shown in A pertains. This is an example of the flame characteristic for a methane combustion. So as you know that methane is the main species of natural gas, and natural gas now is a kind of a booming fuel because of a cheap price, as well as now maybe with the technology, the way we get CH4 or methane is cheaper as well. So in this flame characteristic of methane, we have a high methane on the left side. So because this is unburned zone, okay, so we have a higher methane, and then we also have higher oxygen, so this one. And then as it enters the reaction zone, methane will be consumed or oxidized by oxygen into many species. And you can see in here, as the combustion process occurs, we see some combustion products like CO2, and then we might have some CO inside this flame front, but CO will decrease as it will further oxidize into CO2. But within the flame front with this thickness, this one, so we have a maximum CO as well as maximum hydrogen. But once again, as it's enter the burn zone, hydrogen will also be oxidized into water vapor. And then this is the progress of the temperature. So it starts from unburned temperature here, so TU, and then it will reach the combustion temperature inside this burn zone. In this slide, I will show you the animation of the flame propagation inside the spark ignition engines. You can see in here the spark plug is placed at the center of the cylinder head. We have a J electrode here as well as the central electrode, and then the gaps between the J electrode and the center electrode is where we will have the spark initiation. And this one is the intake system, the left side, and then the green one is the exhaust system, and this one is the seat of the injector. So this one is a GDI engine, so the injection of the gasoline is under the intake system. And the flame propagation here will be shown in terms of the temperature isosurface. It will begins at minus 20 degrees, so this is 20 degrees before top dead center firing. So you will see here the spark initiation, and then the flame propagates, and then it's going toward the wall, and then there will be a quenching process at the wall because of the heat loss or heat transfer to the wall, as well as the species destruction. Okay, let's play once more again. So this one is from the top view, this is from the side view, and we use CFD to simulate this combustion process. Okay. Next one is the flame characterization for the diesel combustion. So in the diesel engine, we have a non-premixed, turbulent, and unsteady flames. So this figure is showing the schematic of the non-premixed flame inside a diesel engine. So this is the structure of sometimes also called diffusion flame. So in this diffusion flame, the fuel and air are initially separated. So in this case, we have a liquid fuel. So liquid fuel is injected through this injector. Okay, and then fuel vapor, in this case, produced within each diesel engine fuel spray. So, but you don't see it here because we only have one fuel spray here. And this vapor is produced due to the evaporation of the liquid fuel drop, and this fuel vapor flows into the inside of the flame. So this is the flame front. So let me put here. So this is the flame front. Okay, and then a chemical reaction occurs where the temperature are highest. So this is where there is just enough air to fully release the fuel chemical energy, and this chemical process occurs inside this flame front. So this green line has a certain thickness, and this thickness is the flame front thickness. And then if we take a look on the zooming of the flame front, let's say somewhere here, then we will have this flame structure. So in this case, we have oxygen. This is from the outside of the fuel spray. Inside the fuel spray, we have a higher fuel, and then there will be a reaction process inside the flame front because we have a composition of oxygen and fuel within the range of the stoichiometric composition. So it is inside this reaction zone where the heat release occurs. And you can also see here that the temperature is also maximum at the center of the flame front. So this one, and then this one will be TU, so the unburned gas temperature. And then here we also have a lower temperature because we still have a lot of fuel here need to be evaporated, so it takes an energy in there, therefore the temperature also decreases here. Next one is ideal gas. So I suggest you to review Thermo 1. I think in chapter 3, I believe, there is one subtopic about ideal gas. Please review it. Or if you have this reference book, go to Appendix B. So there is one appendix talking about ideal gas. And equation 3.1 is one of the form of the ideal gas equation of state. So PV equal to mRT. So P is pressure, V capital here is a volume, and then M here is the mass. so in kilogram or gram, and then R here is the gas constant of the corresponding mixture, okay, and then T is the temperature. And then you can also replace R here as the universal gas constant, so 8314 joule per kilomole Kelvin. You need to divide by the molecular weight of the corresponding gas or mixture and then multiply it by temperature. And then you know from Thermo 2 that mass over molecular weight is moles number. So PV equal to MRT or nRT. So R here is the universal gas constant. In Thermo 2, we also learn several other equation of state. One of these is Redlich-Kwong equation of state. Next one, air and fuel composition. So as I mentioned to you, we use air as the oxidizer of this fuel combustion. For air, in Thermo 2, I think you know wet air, you know dry air. So wet air, it means that air contains some portion of water vapor. Dry air doesn't contain any water vapor. So as shown in this table, so this is a composition of dry air. So you can see there we don't have H2O in this first column. So this is dry air. So within this dry air we have oxygen and then nitrogen. So this two is the main species of dry air. And then we have argon, CO2. And second column here is showing the portion in ppm by volume, and this one is the molecular weight. So oxygen we have 32 or we have 31.998 exact number, and then nitrogen we have 28.02 and so on. Because of a small content of argon and CO2, we can assume that dry air only contains oxygen and nitrogens. And then this is the composition in mole fraction. So we have 21% mole of oxygen and 79% mole of nitrogen. Or it's mean that 1 mole of oxygen is accompanied by 3.773 mole of nitrogen. So we have total mole of 4.773. And these two equations help you to catch the density of air for a given pressure and temperature. So this is assuming an ideal gas equation of state for air species. And then the second formula here is in case you want to get the density in British unit. And then what if we have wet air? Then we use a psychrometric chart to get the properties of this wet air for a given two properties. So this is an example of the psychrometric chart. So I think you know this chart in Thermo 2. So on the vertical axis here we have a kilogram water per kilogram air ratio. I think this is called humidity ratio. And then in this case, in this horizontal axis, you have a dry bulk temperature, and then you have enthalpy, and I believe you have also relative humidity somewhere here. Okay, so once again, you will use a psychrometric chart in case you are dealing with a wet air. What is the impact of the water content to the properties of air? This chart is showing an example of the water content impact to the properties of the air. So in this case we have R, so you can see in here that the gas constant of air increases with the increase of water amount inside the air. So you can see in here that the horizontal axis here is the ratio of water mass to the air mass. And then you can also see here the impact on the CV, CP, so it increases with the water amount. But gamma here is Cp over Cp, Cp over Cv. Gamma decreases with the water content. And then K here, I think it is thermal conductivity. So thermal conductivity decreases with water content inside air. Next one is about the fuel. So for internal combustion engine, we have gasoline or petrol and diesel. These fuel are blends of many different hydrocarbon compounds obtained by refining process. And this fuel are predominantly carbon and hydrogen, so that we have C and H inside each of this fuel. And then in some regions of the world, diesel fuels might contain up to 1% sulfur. And then other fuel of interest, we have alcohol. So within this alcohol, we have methanol, we have ethanol. So we have E10, E15. So it's mean the gasoline contains 10% and 15% of ethanol. We also have a gaseous fuels, and example of this is natural gas. And the main component inside the natural gas is methane. So we can classify different fuels according to their classes. So the first class here is called alkyl compound. So under this alkyl compound, we have paraffin, and then cycloparaffins and olefins. So paraffins is a single bonded open chain saturated hydrocarbon molecules. So it's called saturated because no more hydrogen can be added to this structure. So each C has already 4 arms here, and this is the formula, the chemical formula of this paraffin. So CnH2n plus 2. So an example of this paraffin is isooctane. So it's C818. Okay, so isooctane. Usually it is used as a surrogate for gasoline. We might have also C7H16. So this is N-heptane. This is the surrogate of the diesel fuel. And then the next one is cycloparaffin. So in this case, we have a single bond ring hydrocarbon. Okay, single bond ring hydrocarbon. So it's form a ring here. And this is unsaturated rings, since rings can be broken and additional hydrogen added. So an example of this cycloparaffin. So we have, for example of this, we have, I think, C10H10, or we might have C6H12. So this is the formula of this cycloparaffin. And the next one, we have olefin. So this is an open chain hydrocarbons containing a double bond. So this one is double bond, and this is unsaturated because this double bond can be broken into the single bond, and we can add H into this broken bond. Okay. The next class is called aromatics. So this is the structure of an aromatic. Example of this aromatic is benzene. So benzenes, I think it's C6H6. Okay. This is 1, 2, 3, 4, 5, 6. Okay, this is a benzene. This is the a formula of this aromatic, so CnH2n minus 6. Okay, another example we have is toluene. So toluene, I think it's C7H8, I believe. Okay, the next class it's called alcohol. Okay, so in this compound, one hydroxyl here is OH. So one hydroxyl groups is substituted for one hydrogen atoms. So in this case we have once again one OH as a substitution of one hydrogen atoms. So this is the formula of this alcohol. So CnH2n plus 1 OH. So we might have CH3OH. This is methanol. Okay. We might have C2, okay, H5OH. This is ethanol. So once again ethanol. And you know it's in the fuel station E10, E15. Once again, this is the mixture of 10% and 15% ethanol to the gasoline. Next topic is combustion stoichiometry. This is also a review of Thermo 2 topics. I think the title of the chapter in Thermo 2 is reacting mixture. So in this section, we will study the relations between the composition of the reactants, so in this case fuel and air, in the combustible mixture and the composition of the products. And this relationship depend only on the conservation of mass of each chemical element in the reactants. So if we have sufficient oxygen, hydrocarbon fuel can be completely oxidized. So in this equation 3.3, let's show an example of the propane combustion. So propane, this is C3H8, react with oxygen O2, and then the product is CO2 and H2O. So in this case, we need to make a balance of each chemical element. So let's start with component or with element of B here, parameter of B. So in this case, on the left side we have 3 C atoms, so B also equal to 3. Okay, and then for the hydrogen we have 8 hydrogen atoms on the left side, so we should have also 8 hydrogen atoms on the right side, so that C equals to 4 here. And then A here can be calculated using the balance of oxygen. So we have 6 plus 4, so it means here we have 10 oxygen on the right side. So in this case A must be 5. Okay, so this is an example of the way we balance the mass of each chemical element. So we can generalize this rule by, let's say, having a hydrocarbon fuel of CaHb, this one. So if we react this CaHb fuel with air, okay, and you remember in the previous slide that 1 mole of oxygen is accompanied by 3.773 mole of nitrogen. So we have fuel reacts with air, and then the product on the right side we have CO2, and then we have water vapor, and then we have nitrogen here. Okay, by doing the same thing, you can get what will be the value of A, B, and so on if we know what is the composition formula of the fuel. So this equation 3.5 defines the stoichiometric proportion of fuel and air. So in this case, we have a chemically correct proportion of fuel and air. Therefore, it's also called a stoichiometric reaction. It also means here that we have just enough oxygen for converting fuel into oxidized products. And I put again equation 3.5 at the top here. So using this equation 3.5, we can calculate the ratio of air to fuel. And because this is a stoichiometric reaction, the ratio is also called stoichiometric air-fuel ratio. So this is the mass ratio. We modified the combustion formula for the fuel. So in this case, we have here, we use CHY and Y equals to B over A. Okay, and then you can do the same thing, modified equation 3.5 by using CHY. The stoichiometric air-fuel ratio here is the ratio of the air mass to the fuel mass. So this is the mole number of air, okay, and then this is the molecular weight of oxygen, and then because we have a 3.773 moles of nitrogen, and then this is the molecular weight of nitrogen, then we need to include the whole thing here to be multiplied by the total mole number of air. And then at the bottom here is the mass of fuel. So once again we have CHY, so it means we have 1 C, so 1 mole of C, the mass of C is 1 times the molecular weight of C, 12.011, and this is the mass of hydrogen. So we have Y mole of hydrogen, so the mass of hydrogen is 1.008, this is molecular weight of hydrogen times Y, and we get this one. So equation 3.6 here is the stoichiometric air-fuel ratio of a fuel with the chemical formula or combustion formula of CHY. And based on this equation 3.6, you can see clearly that the stoichiometric air-fuel ratio of fuels depend on the Y, which is the ratio between hydrogen atom number to the carbon atom numbers. So with this equation 3.6, you can make a plot for the stoichiometric air-fuel ratio of different fuel that have a different Y number. And this is an example of the stoichiometric air-fuel ratio plot as a function of fuel molar HC ratio, so actually it's Y. So the stoichiometric air-fuel ratio increases with HC ratio. So we have, let's say, we have somewhere here, it's when Y equal to 1. So an example of the fuel with Y equal to 1 here is benzene. And then on the highest one here, we have HC ratio equal to 4. And the stoichiometric air-fuel ratio is slightly above 17. An example of HC ratio equal to 4 here is methane. Okay, so methane. So you have Y equal to 4 here. So this one. Let's take a look on this example. So in this case, we have a hydrocarbon fuel of composition 84.1% by mass C and 15.9% by mass H, has a molecular weight of 114.15. So this is the molecular weight of the fuel. Okay. Determine the number of moles of air required for stoichiometric combustion and the number of moles of product produced per mole of fuel. Also calculate stoichiometric air-fuel ratio as well as stoichiometric fuel-air ratio and the molecular weight of the reactants and the products. Let's take a look on the solution of this problem. So in this case, we assume that the composition formula of the fuel is CaH8, okay, and then the molecular weight of the fuel is given 114.15. So if we have this fuel, then the molecular weight of the fuel is just the molecular weight of carbons times A plus the molecular weight of hydrogens times B. And then we can make the calculation of the ratio between B and A. So in this case, we have 15.9% by mass. So we can assume that we have 100, let's say 100 gram or 100 kilogram of the fuel, and then 15.9 kilograms or 15.9 grams is hydrogen, and then 84.1 kilogram or gram is carbons. And then if we divide this mass by the molecular weight, it means you have mole, which is here is the ratio between the mole of hydrogen to the mole of carbon. So from the given data, we get B over A equals to 2.25. Then you can use this correlation. You can replace A or B so that this equation will only have one unknown variable, either A or B. Then you can solve it. So you will get A equal to 8 and B equal to 18. So it's mean here the fuel is C8H18. It is isooctane, for example. And then by using equation 3.5, so in this case you have the general combustion equation for the fuel with CaHb. So in this case you have A equal to 8 and then B equal to 18. We react the fuel with air, and then this is the stoichiometric reaction of this C8H18. So for 1 mole of the fuel will need 12.5 moles of air, okay, and it will produce 8 mole of CO2, 9 moles of water vapor, and 47.16 moles of nitrogen. So once we have this stoichiometric reaction, we can calculate the stoichiometric air-fuel ratio and so on. The stoichiometric reaction of the isooctane combustion is shown in this top right side. One observation that you can see here is if you sum up the mole number between reactant and then try to be compared with the mole number for the product, then you can see in here in the reactant you have 60.66 moles, while in the product you have 64.16 moles. So what does it mean here? That for a chemical reaction, the moles number between the reactant and the product are not necessarily the same, okay? What must be the same is the mass, okay? If you check the mass for the reactant and the mass for the product, they are the same, okay? They are the same. So this means in this reacting case that the mass conservation must be fulfilled. Okay, and then if you, let's say, normalize this fuel mass, so it's mean here you normalize to get it to be 1. So it's mean that on each term of this equation you divide it by 114.5, then you will get this one, that for 1 kilogram of fuel, in this case isooctane, will need 15.14 kilogram of air to produce 16.4 kilogram of the product. So thus, for stoichiometric combustion, in this case you have 1 mole of fuel required 59.6 mole of air from this one, from this reaction. So you can see there that 1 mole of fuel requires 59.66 mole of air and produce 64.16 moles of the product. Okay, and then from this equation, you know that the stoichiometric air fuel ratio, so it means this is the ratio between air mass to the fuel mass, so it means this one is 15.14 divided by 1, so you have this one. This is the stoichiometric air fuel ratio, and then the stoichiometric fuel to air ratio is just the inverse of this stoichiometric air ratio. This is 0.0661. And then the molecular weight of the reactant, so Mr, and the product Mp, can be calculated by using this formula. So I think this is available in Thermo 2. So in this case, you sum up the mole number for each species in the reactant times its molecular weights, and then divided by the total mole number of the reactant. So in this case, we have Mr of 30.36 kilogram per kilomole, and then Mp is 28.71 kilogram per kilomole. Next topics is excess air and less air. We have studied this one in Thermo 2 as well. So a fuel air mixture with more than or less than the stoichiometric air requirement can be burned. Okay, so in this case we do not need to have an exact stoichiometric composition to have a fuel air combustion. So we can add more fuel slightly, or we can reduce fuel amount slightly as well. So for example, we have isooctane, so C8818, and then in this case we burn this isooctane with this, you can see in here, with 25% more of air. So you can see there it's multiplied by 1.25, because this is the stoichiometric mole number of air for each 1 mole of the fuel. So once again, if we combust this isooctane with 25% more air, then we have equation 3.7. So in this case, we have 8 mole of CO2, and then we have 9 moles of water vapor. And you can see in here, because we have more air, so there is additional species on the right side here, which is oxygen. So in this case, we have 3.13 mole of oxygen plus the nitrogen. So there are parameters, two parameters actually, that can be used to represent or to know how much is the deviation of the fuel reaction from its stoichiometric reaction. First parameter is called equivalent ratio. So the letter used to represent equivalent ratio here is the Greek letter, so it is phi. So phi is the ratio between the actual fuel air ratio to the stoichiometric fuel air ratio. You can also write it on this one as the air fuel ratio stoichiometric over air fuel ratio actual. Okay, same thing. Okay, And then the inverse of phi is called relative air-fuel ratio, and it is represented by lambda. Okay, so lambda is the inverse of phi. So you can use either phi or lambda again to represent once again by how much this actual reaction deviates from its stoichiometric reaction. In Thermo 2, we learn a bit about fuel-lean mixture and then stoichiometric mixture and fuel-rich mixture. Fuel-lean mixtures means when the amount of fuel is less than its stoichiometric amount. And then fuel-rich mixture means that the fuel amount is higher than its stoichiometric amounts. For fuel-lean mixture, it means that we have lambda less than 1, lambda more than 1, or phi less than 1. Okay, for stoichiometric mixture, phi equal to lambda equal to 1. And then for fuel-rich mixture, phi is more than 1 and lambda is less than 1. How about fuel with oxygen like methanol, ethanol? So the procedure for determining the overall combustion equation is the same, except that fuel oxygen is included in the oxygen balance between reactants and products. And this is an example of the combustion process, stoichiometric combustion for methanol or methyl alcohol. So this is the methanol chemical formula. Okay, so we have CH3OH. So 1 mole methanol requires 1.5 mole of air. Okay, and then so in this case, when we balance oxygen, we need to include this O within the fuel. And you can do the same thing for ethanol, uh, propanol, and so on. Next topic is first law of thermodynamics. This is also a review of Thermo 2 topics. In a combustion process, we have fuel and oxidizer that react to produce products of a different composition. This is the reason that we need to have a different strategy when using enthalpy or internal energy for energy balance analysis. The first law of thermodynamics relates change in internal energy or enthalpy to heat and work transfer interaction. So you can see the schematic here. We have an initial state reactant. So it means the system initially only contains reactant at a certain temperature. So Tr, certain pressure Pr, and then volume is Vr, and internal energy of Ur. And then there will be a combustion process. And then during this process, the work might be produced, the heat transfer with the environment might happens as well. And then the final stage, we have a product, let's say 100% product with temperature of Tp, pressure of Pp, and then volume of Vp, and the internal energy of Up. Using the first law of thermodynamics, we can relate this internal energy change between the initial and final state to the heat transfer and the work produced or generated during the process. Equation 3.13. So QRP minus WRP equals to UP minus UR. So in this case, we assume that Q is positive when it's come to the system, and then the work is positive when the system is doing work. And then we put the equation again on this side. So for constant volume process with a constant temperature, so it's mean we don't have Tv. So in this case, this will drop W. Then we have equation 3.14. So QRP is balanced by delta U. Okay, and we know that combustion process is an exothermic process. So QRP and delta UVT are negative. So it's mean here the heat transfer is from the system going into the environment. And then minus delta U at a constant volume and constant temperature is known as the heat of reaction at constant volume at temperature T prime here. Okay, and then for a constant pressure process with constant temperature, then work is not zero anymore. So in this case, we have equation 3.15 for the formula of work. So P times dV. dV here is Vp minus Vr. And then we can substitute a WRP with this one and put it here. Then we can adjust the term a little bit. You will get equation 3.16. So in this case, QRP is balanced by delta H. Okay, so you know in thermo 1 that enthalpy is the sum of internal energy and pressure times volume. Okay, and then the next one is that the difference between delta U PT, so this is at constant pressure at temperature T prime, and delta U VT, so this is at constant volume and temperature of T prime, is this one, PdV, okay, equation 3.17. And then we can replace this PV if we can assume that the mixture follow ideal gas, then we have this one, R times N times T, but in here you have a Vp minus Vr, so you have this one, N prime P minus M prime R. And on the right side here, you can see the schematic of U and H dependency on the temperature. Okay, so we have two lines here. Line number 1 here is for the reactant, and then line number 2 is for the product. Okay, and then if we have a reaction at T0, okay, and the difference between this point and this point, okay, it's called this one, delta UV or delta HP at temperature T0. And then this is the same thing, but at temperature T prime, okay? And you can see in here, as the temperature increases, the difference decreases, because you can see in here, the slope for this two line make this line try to be closer with a higher temperature. The combustion product of H2O can be in the gaseous or liquid phase, and the difference of delta U when H2O in the gaseous to the delta U when the H2O in the liquid equals to the heat of evaporation of water. So we have equation 3.19 when we analyze this difference in delta U, or equation 3.20 when we analyze the difference in enthalpy. And the figure on the bottom side here is showing the schematic of this delta U and delta H different when H2O in the gaseous or liquid phase. So on the left side, so we have U here, okay, and then this is the line for the reactant U, and this one is for the product, and you have two lines here, and then the upper side here is when the water or the H2O in gaseous phase, so this one, and then the second one, the bottom side here, is when H2O in the liquid phase. Similarly, we might have a fuel in liquid phase or fuel in gaseous phase, and we can do the same thing here. You can see on the right side here we have two lines for the reactant. So the first line here is when the fuel in the gaseous phase, and the second one here is when the fuel in the liquid phase. And the difference between these two lines, blue and red, is the evaporation energy of the fuel. Next one is enthalpies of formation. This parameter was introduced to solve the problem of the enthalpy or internal energy datum for a reacting mixture. For fuel that are single hydrocarbon compound, the enthalpy of the reactants and the products can be related through the enthalpy of formation. In this case, the enthalpy of formation of a chemical compound is the enthalpy increase associated with the reaction of forming 1 mole of the given compound from its element, with each substance in its thermodynamic standard at the given temperature. Usually the standard condition is 25 degrees C and 1 atmosphere or 1 bar. There is another rule here that the enthalpy of formation for stable element is 0. Stable element here is what is the composition or what is the chemical structure of the corresponding species at the standard condition. Like oxygen, at the standard condition, oxygen has the combustion formula of O2. So it means the enthalpy of formation of O2 equals to 0. But for single O, it is not 0, okay? Because single O is not a stable element at 25 degrees C and 1 atmosphere. And this enthalpy of formation data is available in Janov table and others. And we know that there is a table in Thermo 2 reference book, so at the end of the books, that contains this enthalpy of formation for a certain species. And this table 3.2 is showing the enthalpy of formation for certain species, for example, like oxygen, you know, O2, it has a 0 enthalpy of formation, and then N2 as well, H2, and then C, they have a 0 enthalpy of formation, and then CO2 has a minus 393.52 megajoule per kilomole enthalpy of formation. Okay, and then we have two equations here to calculate the enthalpy, total enthalpy of the product. This one is for the reactant, and then the enthalpy increase is just the difference between HP and HR, and this sign means that it is conducted at a reference condition, so 25 degrees C and 1 atmosphere. Let's take a look on this example. Calculate the enthalpy of products and reactants and the enthalpy increase and internal energy increase of the reaction of a stoichiometric mixture of methane and oxygen at 298.15 Kelvin. So this is also 25 degrees C at standard condition. So methane is CH4. So this one equals to 25 degrees C. Okay, we use table 3.2 to get the enthalpy of formation for CH4 and then CO2 and H2O. And equation 3.18 will be used to calculate the enthalpy increase and internal energy increase. So this is the schematic reaction of methane. So 1 mole of methane requires 2 mole of oxygen, producing 1 mole of CO2 and 2 mole of H2O. And then for gaseous H2O, okay, from table 3.2, we need to take this one, okay? That's the enthalpy of formation of H2O in gas phase is minus 241.83 megajoule per kilomole. So we can get HP of minus 877.18 megajoule per kilomole CH4. And then for H2O in liquid phase, then we use this data. We get HP of minus 965.2 megajoule per kilomole CH4. And then for the reactant, we only consider the enthalpy of formation of CH4, so minus 74.87, okay, because the enthalpy of formation for O2 here equals to 0, okay. So the enthalpy increase here for H2O in gaseous phase is this one, and for for H2O in liquid phase we have this one. And then the next one is to calculate the internal energy increase. We can use the correlation of ideal gas, okay. So, or yeah, this one is coming from the ideal gas correlation. So we already have delta H, and then we need to calculate what is delta U. So we have temperature, and then you can see in here that it's pretty much also depend on the NP and NR. So if you look at this chemical formula, if we have a gaseous H2O, then we have 3 mole of the product and 3 mole of the reactant. So what does mean here? When H2O in a gaseous phase, so delta U equal to delta H, okay? This is because NP equal to NR. If or when the water in liquid phase, then we only have 1 mole in the product and 3 mole in the reactant. Then in this case, delta U does not equals to delta H. So we have a delta U here of minus 885.4 megajoule per kilomole CH4. So we have used a reaction mechanism to get the lower heating value of certain fuel. For fuels where the precise fuel composition is not known, like gasoline, so gasoline consists of several species, and we cannot use the previous method to get the gasoline lower heating value or gasoline higher heating value. So in this case, we need to use an experimental method to get the heating value of the gasoline fuel. And the heating value, QHV, or calorific value of a fuel, is the magnitude of the heat of reaction at constant pressure or at constant volume at standard temperature, so 25 degrees C or 77 degrees Fahrenheit, for the complete combustion of unit mass of the fuel. So you can see in here we have 2 equations here, which is pretty much the same as the previous equation, but in this case we use test data, or we use a measurement to get the heating value of the fuel when it doesn't have a precise composition. For fuels containing hydrogens, H2O product can be in the liquid or gaseous phase. So because of this, we have 2 types of heating value. One is higher heating value. This is when H2O product in the liquid phase. The second one is lower heating value. This is when H2O product in the gaseous phase. So we have HHV, higher heating value. We also have LHV, lower heating value. And the difference between HHV and LHV is the heat of H2O evaporation. And you can have a look for the heating value of different fuel in the appendix D or even you can open one of the table in thermo books. But don't worry, when we need this in the exam, I will keep the table in the exam as well. And this is the heating value. I think I took this one from thermobook. So you can see in here we have a gasoline, and then we have E10. So it's mean gasoline with 10% of ethanol. And then we have light diesel, and then you need to pay attention on this one, lower heating value, this one. Okay, for example, like gasoline. Gasoline has a lower heating value of 43 megajoule per kilogram. When we add 10% ethanol to the gasoline, the lower heating value drops to 41.5 megajoule per kilogram. So this is because ethanol has a lower heating value than gasoline. I think we have ethanol. Okay, see here, this is the lower heating value of ethanol, only 26.9 megajoule per kilogram. On this table, you can also see the lower heating value for natural gas, which is mainly methane. And then but you also have methane lower heating value, propane, and so on. Okay, and this one, oh, this one is from the thermo book, sorry. So the previous one is from appendix D of the internal combustion engine books, and this one is coming from thermo books. Okay, so same thing. So you need to pay attention on the last column here. So this is the HHV and LHV of different fuel here. So you have, oh, you even have a single carbon here, and then you have hydrogen. Oh, you have ammonia here. So this might be a future fuel, ammonia. Okay, so it doesn't have a C there, so it means you won't have a CO2 emission from ammonia combustion. And then we have butane, pentane, and so on. The last one here, you have alcohol fuel, methanol, ethanol, and so on. Okay, let's take a look on this example. We have a liquid kerosene here with a lower heating value. So it is from the test data using a calorimeter of 43.2 megajoule per kilogram. And then a kerosene has an average molar HC ratio of 2. Kerosene is mixed with the stoichiometric air requirement at standard temperature, so 25 degrees C or 298.15 Kelvin. The question is, calculate the enthalpy of the reactant mixture relative to the datum of zero enthalpy for C, O2, N2, and H2 at a standard temperature. Okay, we have kerosene, so CH2, okay, and then react with air. From this stoichiometric reaction, you can see that 1 mole of kerosene required 1.5 mole of air. Okay, let me check my pen stop working here. Okay, so we have 1 mole here, and then it required 1.5 mole of air. In the product, we have 1 mole of CO2, 1 mole of H2O, and 5.66 mole of nitrogen. Okay, and then you can see in here for the mass balance, we have 14 kilogram of fuel, required 207.4 kilogram of air, and the product we have 221.4 kilogram. And this is the molecular weight of atmospheric air, 28.962. Okay, so first we need to calculate delta HP. Okay, so with the same method. Okay, so in this case we use equation 3.18. this one, okay, that delta H equal to delta U plus R times delta N times T, okay. So this is, I think, the mole number for product, okay, yes, correct here. And then this is the mole number for the reactant, okay, for the reactant. And then this is the temperature, I think. So you will get delta H P, so this is at constant pressure of minus 43.1 megajoule per kilogram fuel, okay. And then, so why don't we include the mole number of kerosene? So you can see in here that the mole number of reactant is only 7.16. This is coming from the mole number of air. Why don't we include this one? This is because this kerosene is in liquid phase, okay? And then the enthalpy of the products per kilogram of mixture is found from the enthalpies of formation of CO2 and H2O, okay, using this table 3.2. Okay, you will get HP of minus 2.87 megajoule per kilogram, and then HR here, HR equal to HP minus delta HP, okay. So you will get HR of minus 0.145 megajoule per kilogram. And then adiabatic flame temperature, it should be a quick review from Thermo 2. So adiabatic process, so it's mean Q equals to 0. So in this case, we have UR equals to UP. And then the temperature of the product at TP here is called adiabatic flame temperature. Okay. And this plot is showing the dependency of adiabatic flame temperature to the equivalent ratio phi. And you can see in here that adiabatic flame temperature is maximum when phi is 1. Okay, so it's mean you have maybe slightly higher than 1, so maybe 1 point something. So this is the maximum one, but it's close to phi of 1 here, stoichiometric combustion. Next one, combustion efficiency. In practice, the exhaust gas of an internal combustion engine contains incomplete combustion products. So we have CO, we have H2, unburned hydrocarbon, soot, and so on. So it's mean we don't burn the fuel completely. So there is some unburned fuel at the end of the combustion process. So a fraction of the fuel chemical energy, it's not fully released inside the engine during combustion process. So this showing a schematic of the engine system. We have a fuel entering the system as well as air entering the system, and then we have the exhaust gas. So we might still have a few amount of fuel leaving the system because it was not burned. And in this case, we have a parameter is called combustion efficiency. So this combustion efficiency represent the ratio between enthalpy of the reactant and enthalpy of the product divided by the fuel energy. So fuel energy is the multiplication of the fuel mass and fuel heating value. Okay. And this chart is showing the impact of equivalent ratio to the combustion efficiency. So we have two types of data here. Cross here is for the diesel, and then diamond here is for the spark ignition. So diesel engine usually operates on lean mixture combustion, so it's mean phi is lower than 1, and it has a high combustion efficiency. And then spark ignition engine usually operate at stoichiometric mixture as well as leans and rich mixture. And you can see in here, when we have a rich mixture, the combustion efficiency drop. So even here up to 70% here. Okay, so from this data you can see that generally diesel engine has a better combustion efficiency than SI engines. Next one is chemically reacting gas mixtures. I think this is the last topic of this chapter. Depending on the process under consideration and the portion of the engine cycle in which it occurs, chemical reactions may be so slow that they have a negligible effect on mixture composition. So in this case, the mixture composition is essentially frozen. An example of this is the chemical reaction process during the intake stroke, during the combustion stroke. So the temperature is low so that the chemical reaction is so slow. Okay. The second option is that the chemical reaction may be so rapid that as the mixture state changes, the composition remains in equilibrium. So, but this second option has a very low possibility in the combustion process within the internal combustion engine. The third option is that the chemical reaction may be one of the rate controlling processes that determine how the composition of the mixture changes with the time. This is what happened during the combustion process inside the internal combustion engine. Okay, so this is what happened in actual process. This is what's going on during the intake stroke, during the combustion stroke. This is the idealization. So if we do let's say like a modeling and want to solve this in a quick time, we can assume that a chemical equilibrium state is attained. Okay, chemical processes in engines are often not equilibrium. Okay, so I think most of the time, or even all the time, is not in equilibrium. So in this case, the time constant of the controlling chemical reaction are not short, okay, compared to the time scale over which the system condition change. Okay, and then the rate at which a chemical reaction proceeds depend on the concentration of the reactant, temperature, and whether any catalyst is present. This makes sense. Okay, so whether you have stoichiometric combustion or you have Lins mixture combustion, it will govern the speed of the chemical reaction. Okay, and in this case we have what is called here is chemical kinetic. So okay, and I think we also learned this reactant mixture along with the chemical reaction in Thermo 2. Okay, how about the chemical reaction of the fuel in actual process? It is very complicated. So uh, the case when we have like CH18 plus air, and then in the product we have CO2, H2O, and so on. This is a global reaction, and this is a simplification. So in real chemical process, we have a lot of chemical paths before this fuel is converted to CO2 and water vapor and so on. So this chemical path is showing example of isooctane combustion with oxygen. So you can see in here we have a path going to this direction as well as going to this direction, and it is controlled by the temperature, it is controlled by the amount of oxygen, and so on and so on. And this one is just showing the block of initiation reaction, and we have another blocks for the high temperature reaction and so on. Okay, and there is one subject that deal with this reaction mechanism, and usually it is offered in the master degree and PhD degree levels. And this is an example of the reaction mechanism for isooctane published by several authors. So starting from the simple one here, Shell published isooctane reaction mechanism with only 5 species and 8 reaction, and it's shown the range of reaction mechanism applicability, so temperature range, pressure range, and then equivalent ratio range, and then the year it was published. And it's going down here, we have more complicated reaction mechanism, for example like the one from LLNL. So this is one of a national lab. So for this isooctane, LLNL develop a reaction mechanism with 857 species and 3,606 reaction, and this is the applicability of the reaction. And I think next year there will be one more reaction here. This is Suri, and I'm the lead author for this one, and we call this one is hedge mechanism. Actually we developed this one is in I think 2017, but we need to hold this reaction mechanism for 4 years, okay, because of the client who support this research. So this hedge mechanism is good for gasoline combustion under a very high EGR condition. So here we might have around 30%. Okay, we have completed this chapter 3 discussion. Thank you, and you have a great day.